Hello, now we solve example 5. So for the velocity field with b equal to 0, we have u equal to ax square minus y square, v equal to minus 2axy, and w is equal to a constant b, which is equal to 0. Determine under what conditions this is a solution to the Navier-Stokes equations, and assuming that these conditions are met, determine the resulting pressure distribution when z is up, gx equal to 0, gy is equal to 0, and gz equal to minus g. So first we need to see if the velocity field satisfies the continuity equation. So this is an incompressible flow, so the continuity equation should be del u over del x plus del v over del y plus del w over del z is equal to 0. So we need to see if this should be equal to 0. So del u over del x is 2ax, and del v over del y is minus 2ax, and del w over del z is 0. So 2ax minus 2ax is equal to 0. Then the continuity equation is verified. Of course, if the continuity equation is not verified, we should stop there and not continue the problem. So first we start with the x momentum equation. Rho gx minus del p over del x plus mu into second derivative of u with respect to x plus second derivative of u with respect to y plus second derivative of u with respect to z equal to rho into the acceleration in the x direction, del u over del t plus u del u over del x plus v del u over del y plus w del u over del z. Since gx is equal to 0, then the term rho gx will vanish, so we'll obtain minus del p over del x plus mu. The second derivative of u with respect to x is 2a, and the second derivative of u with respect to y is minus 2a, and u is independent of z, so the second derivative with respect to z is equal to 0. So is this equal to rho into del u over del t is 0 plus u ax square minus y square into del u over del x is 2ax plus v, which is minus 2axy, into del u over del y, which is minus 2ay, plus w is 0, so the last term will be equal to 0. Then we will obtain minus del p over del x is equal to rho into, we'll have 2a square x into x square minus y square plus 4a square xy square. So this would be equal to rho into 2a square x cube minus 2a square xy square plus 4a square x y square. So here we have minus 2a square xy square plus 4a square xy square. So del p over del x is minus rho into 2a square x cube plus 2a square x y square, since minus 2a square xy square plus 4a square xy square is equal to 2 into a square x y square. So we can take 2a square as common factor, so minus 2a square rho common factor into x cube plus x y square. So we'll obtain that the partial derivative of the pressure with respect to x is equal to minus 2a square rho into x cube plus x y square. Now we apply the y momentum equation. We have rho gy minus del p over del y plus mu second derivative of v with respect to x plus second derivative of v with respect to y plus second derivative of v with respect to z equal to rho into the acceleration in the y direction del v over del t plus u del v over del x plus v del v over del y plus w del v over del z. So gy is equal to 0, the first term is equal to 0, minus del p over del y plus mu second derivative of v with respect to x. So v is minus 2axy, so let's write v here, minus 2axy. So the second derivative of v with respect to x is equal to 0, and the second derivative of v with respect to y is 0, and with respect to z is 0. So rho into del v over del t is 0, plus u, which is a into x square minus y square, into del v over del x, which is minus 2ay, plus v minus 2axy, into del v over del y, which is minus 2ax, so into minus 2ax, plus w, which is equal to 0. Then we will obtain del p over del y is equal to minus rho into minus 2a square y into x square plus 2a square into y cube, and then plus 4 into a square x square y. So minus 2a square x square y plus 4a square x square y is 2a square x square y. So we'll have minus rho into 2a square x square y plus 2a square y cube. So we can take minus 2a square rho common factor, minus 2a square rho as common factor. So we will obtain between the brackets x square y plus y cube. So this is the partial derivative of p with respect to y. Now the last momentum equation, in the z direction, we'll have rho gz minus del p over del z plus mu the second derivative of w with respect to x plus the second derivative of w with respect to y plus the second derivative of w with respect to z. It is equal to rho into the acceleration in the z direction del w over del t plus u del w over del x plus v del w over del y plus w into del w over del z. So gz is equal to minus g, since z is up and g is down. So we'll have minus rho g minus del p over del z plus mu into 0, since w is 0, and of course all the acceleration terms are equal to 0. So we'll have del p over del z is equal to minus rho g. So this reminds us of the hydrostatic pressure distribution, since the fluid is not moving in the z direction. So in the z direction we have a hydrostatic pressure distribution. So as a summary of the result, we have del p over del x is equal to minus 2a square rho into x cube plus xy square, and del p over del y is equal to minus 2a square rho into x square y plus y cube, and del p over del z is equal to minus rho g. So for p to be a smooth function of x, y, and z, or for p to be a valid solution, it should be a continuous smooth function of x, y, and z. There should be no discontinuities in the pressure function, or this solution will be not valid. So it should be a smooth continuous function of x, y, and z. So for a smooth continuous function of x, y, and z, the mixed derivative del over del x of del p over del y should be equal to del over del y into del p over del x. So the order of differentiation should not matter in a continuous function. So to determine whether p is a smooth continuous function, the two mixed derivatives should be equal. It's not necessary to check on the z, so not necessary to check on del over del x of del p over del z if it is equal to del over del z of del p over del x, because it's obvious the mixed derivative with respect to z is equal to 0. So we need only to check on x and y. So del over del x of del p over del y, it is derivative of the partial derivative with respect to y, so it is equal to minus 2a square rho into 2xy, so minus 4a square rho xy. Now we differentiate with respect to y del p over del x, so we look at del p over del x, which is equal to minus 2a square rho into x cube plus xy square, and we compute the differentiation with respect to y. So this will be equal to also minus 4a square rho into x y. So as you can see, the order of differentiation doesn't matter. So del over del x of del p over del y is equal to del over del y of del p over del x. That means that the pressure is a valid solution in the Navier-Stokes equations, and the pressure in this case is a smooth function of x, y, and z. Now let's try to determine the pressure field function of x, y, and z. So if we start with the partial derivative of p with respect to x, which is equal to minus 2a square rho into x cube plus xy square, then we partially integrate with respect to x, minus 2a square rho into x cube plus xy square dx. So if we do the integration, we will obtain minus 2a square into rho into x4 over 4 plus x square y square over 2 plus function of 1, which is function of y and z, the other variables that we did not perform the integration on. So we performed the integration on x, so the other variable will be function of y and z. So if we now compute the partial derivative of p x, y, z with respect to y, we will obtain minus 2a square rho into x square y plus del f1 over del y. And we equate this result to the original expression for the partial derivative with respect to y. So which is equal to minus 2a square rho into x square y plus y cube. So using this identity we can obtain an expression for del f1 over del y. Then in this case del f1 over del y will be equal to minus 2a square rho into y cube. Then if we partially integrate f1 with respect to y, so f1, which is a function of y and z, equal to the integral of minus 2a square rho into y cube dy, which is equal to minus 2a square rho y4 over 4 plus another function f2, which is a function of z. So since we partially integrated with respect to y, so the other function will be a function of z. Now we back to this pressure expression and we differentiate with respect to z. So the first term will be equal to 0 and we just obtain del f1 over del z, and del f1 over del z is equal to del of 2 over del z, since the first term minus 2a square rho y4 over 4 is independent of z. And we know that del p over del z is equal to minus rho g, so equal to minus rho g. Then we can say that f2, so del f2 over del z equal to minus rho g, then f2, which is a function of z only, is equal to integral minus rho g dz. So it will be equal to minus rho gz plus a constant of integration. Then in this case f1, which is a function of y and z, is equal to minus rho a square y4 over 2 plus f2, which is minus rho gz plus the constant of integration. Then p in this case, which is function of x, y, z, will be equal to this expression. So minus rho a square into x4 over 2 and minus rho a square into x square y square plus f1, which is minus rho a square y4 over 2 minus rho gz plus the constant of integration. Now we can take as common factor, can rewrite this expression and take as common factor. So let's first put minus rho gz and minus half rho a square as common factor. So we will obtain x4 and plus y4 and plus 2x square y square plus the constant c. So this constant can be easily identified by taking the pressure at the point 0, 0, 0. So at 0, 0, 0 all these terms will vanish and we will obtain that the constant is just the pressure at the point 0, 0, 0. Then p, the function p, which is function of x, y, z, will be equal to minus rho gz minus half rho a square into x4 plus y4 plus 2x square y square plus the pressure at the point 0, 0, 0.